Alright, as I always do with these Heathkit test equipment videos, I'm going to start out with Chuck Penson's excellent book, Heathkit Test Equipment Products. So I go to the chapter on audio equipment, and that means audio test equipment, not like stereo systems. Chuck actually has a separate book for Heathkit audio equipment, meaning hi-fi and stereo stuff. So we get past all the frequency meters and sine wave audio generators and things like that, which are the first couple of pages here. And we get to the HD1. This is a harmonic distortion meter produced by Heathkit starting in 1955 and continued through 1962. Cost $49.50 back then, a fairly decent chunk of money. Useful in the design and servicing of audio amplifiers, but can also be used to measure distortion in receivers and transmission lines. Heath claimed that with the use of a high-quality microphone, the HD1 can even be used to check for distortion being introduced by speakers in an audio system. Heath noted that with the use of an audio signal generator, it would have to be a sine wave generator, the HD1 can measure distortion on any or all frequencies between 20 and 20,000 Hertz. In other words, 20 and 20 kilohertz. Thus, a complete family of distortion curves may be compiled. So this product was the same circuit as what we're looking at here, because in 1962 it was replaced by the IM-12, which is what we have here. So it's just the same thing. It's a restyling. They changed the cosmetic stuff but left the circuit totally alone. You can see this has gray plastic knobs and a meter that's square in shape or rectangular, and it has a solid dark gray front panel. When we went to the IM-12, they had changed their industrial design look a little bit. They had a silver or light gray band around the front. The meter had a sexier looking, or at least what people thought was at that time, sort of raked in sides a little bit, looked more dynamic, and they went to the black knobs with the metal inserts on them. Otherwise, if you take the front panel off, it's exactly the same meter as the HD1 that came before it. No changes at all. This was made from 1962 through 1968. After that was discontinued, the next year in 1969, the IM-58 came out, and that was continued through 1976. I haven't checked it personally. I have compared the schematics for the first two, and they are indeed exactly the same. So purely a styling difference. But I should note that both of the earlier ones, the HD1 and the IM-12, have the indicator light right up here on this little bump at the top of the meter movement. Whereas they switched to this type of meter movement on the IM-58 with a black bottom on the meter, still a rectangle, and they didn't have the little pilot light in it. Instead, they put a separate pilot light over here. That's the only real difference. And now they're into this beige coloration with the beige knobs. So again, just changing it to look like the other equipment of the era stylistically, but this says that it's the same circuit identically, and it probably is. Even though the pilot light moved, it's still the same type of light bulb, I'm sure, and connected to the same place in the circuit. There's no specification changes or circuit changes. If you have a good working meter that suits your clientele, why change the design? Just update it so it looks like it belongs with the other stuff they're selling in that decade or whatever. Now, by this time into the 76, we're into the period when people are like, vacuum tubes, you know. So Heath finally did design the IM-5258, which came out the same year as the IM-58 was discontinued, and they made it up through 1983, you know, into the waning years of Heathkit. They did not make any other distortion meters after this. But this one is not a vacuum tube circuit. It still works the same basic way. It still has about the same knobs on it. It has the big tuning knob, and all these other ones had the tuning knob and then 1, 2, 3, 4 knobs for making adjustments. And this one has 1, 2, 3, 4 knobs for making adjustments, and then there's a power switch. I think this is actually a power switch. Anyway, whatever it is, it does the same thing and it essentially has the same controls. But basically it's the same thing, just using solid state amplifiers instead of vacuum tube amplifiers. Alright, here's the artifact. This is one of the bigger pieces of test equipment I've had on my bench from Heathkit anyway. It's going to be a little awkward to work on just because of its size. The meter face is a little bleached out. The red scale is visible, but not as much as it would have been when new. It's pretty dirty. A lot of grub in the knurls. The knobs and pots turn, except this one, the switch seems loose and kind of, I can feel the whole switch moving inside rather than turning, so that's going to need some attention. Other than that, the case looks like it's reasonably intact, and there's not any real damage to it. A little bit of discoloration here, which I'll probably just clean off. I probably won't have to repaint this. Well, I misinterpreted the signs. Turns out this is not a knob. Kind of a daffy thing for Heathkit to do. This is more like tuning a radio, and this is the actual tuning knob down here that turns freely. And inside, you've got a great big wheel here, which is on the same shaft that this apparently stuck knob is on, and that goes to this big tuning capacitor. And then around the wheel is a cord which goes down and wraps around the axle for this knob here, the tuning knob. So what actually happens is when turning that knob, it turns this big wheel. So this is like a fine-tuning thing. You have to turn it a bunch of times to turn the big wheel. And then when the big wheel turns, this moves and points, so it's a rough frequency indicator of where you're tuning it to, but it is not a knob that you can turn yourself because it's overwhelmed by the friction of the cord and the gearing down of the big wheel to the tiny wheel here. You just can't overcome the friction on it. So there's nothing actually broken here. The reason it felt loose was because the knob was loose on the shaft. So I think all that's good. I took off the shield so I could see what was inside this box, and it was exactly what I thought, just a big capacitor, adjustable capacitor. There's a big multi-electrolytic capacitor here. 1, 2, 3, 4, 5, 6 vacuum tubes. The meter with some sort of a board on it with some diodes and resistors. And the socket for the indicator bulb for power on. And power transformer. And it really is done with old-fashioned point-to-point wiring. Oh, there's also a adjustability point on the back. There's a hole in the back of the case, and there's a good old-fashioned, looks like a wire-wound rheostat potentiometer arrangement on there. With something this old, there's a good chance that some of the resistors will be out of whack. So I'm going to have to test some of those to see if they're too far out of tolerance. They are only 10% resistors to start with, so probably not many of them are all that critical in terms of value. There's also, in addition to the capacitor here, which I thought was a multi-point capacitor, but it looks like there's only the can and one lead, so it's just a single capacitor. And then an old paper electrolytic here, which has certainly gone to meet its maker. There's also two more wire-wound potentiometers on the case there, which can be adjusted with controls there through the top. So not too complicated of a circuit. Some wire-wound resistors on the sensitivity switch, carbon potentiometer there for the level adjust. Yeah, I mean, assuming that I get this thing recapped, and this is also going to need changing here, this guy, and this one probably too. Those usually don't survive very well, so an order to digikey will be in line. All the other capacitors seem to be disc capacitors. Those usually last just about forever. And I'll have to make sure that the tubes are working. They probably are. So it'll take some cleanup and some messing around with. I have a manual on order. So once I get that, I can start doing some work on this. But I can get my capacitor order going right away, so at least I have those on hand. And this capacitor is actually two capacitors in one package. It's a dual 20 microfarad, what is it, 350 volt? 350 volt capacitor. So that'll take two to replace it. With that resistor across between them, it's probably a pi filter. And this is what's underneath the tuning capacitor. It's the gang of the range switch with a bunch of wire-wound resistors. Now there's a component down there. I don't think that's a capacitor, but I'll have to check, see if that's something I need to replace. Well, I've been going through this, checking all the resistors, except for the wire wounds, and even a lot of those. And only one of them seems to be out of whack, and that's this should be 2700 ohms. It's way down in here where I'm pointing. I actually cut the lead here, right there, so I could make sure there was no other thing in parallel with it. And it's about twice, well, it's about 5,000 ohms, so it's way out of tolerance. Everything else was within tolerance, which surprised me. All the carbon comp resistors. So I'm definitely going to have to replace that one, but something else that was stymieing me was trying to figure out this part of the schematic here with the range switch and all its resistors and contacts and the trim capacitor and this funky looking little white radial lead thing down there, which is actually a 4.7 picofarad capacitor. Don't know what type, but it's probably okay. And then the two halves of the tuning capacitor that it doesn't have any markings on the schematic, and I had to trace out the assembly instructions in the manual to figure out that this terminal, where the wire goes to the insulator into the tuning cap down there, that's what they call terminal 2 in the assembly instructions. And this hole over here is what they call terminal 1. And I found out those are internally connected together inside the tuning capacitor. So that point there and this point here are electrically the same thing. So that cleared up some of the confusion in the schematic. I thought those were different parts of the capacitor. And then this one down here that they call 3 in the assembly instructions does go to all the things it's supposed to. It goes to the fixed capacitor, it goes up to the switch, it goes to a drop my paper on the ground, goes to a 1 meg carbon comp resistor, which goes to a terminal which is not grounded, and through a wire it runs over here and goes to tube pin, the 12AX7 tube pin 2. That's this white wire that comes along this way. So that's coming from that 1 meg resistor. Well, this would be that 1 meg resistor, and it's definitely coming from the low side or terminal 3 of the capacitor, but the way it's wired, it does not go to circuit ground or chassis ground, which is this wire here. Instead, it ends up going to pin 2 of the 12AX7, which is exactly where it looks like it's going here. And then that jumpers over to pin 8 on the 5879, and that's this wire here. So pin 2 on that tube goes to pin 8 on this tube, and that's what's shown. And there should be a 100K from that to V plus, essentially. So terminal 8, yeah, there is that 100K, and it's going up here to terminal 1 of the 12AX7. Terminal 1 on the 12AX7 does go to V plus. So all of that's correct, but that 1 meg resistor should not be going to that. The only things going to that node are pin 2 of the 12AX7, pin 8 of the 5879, and that 100K resistor. Nothing else should be going there. But the way this thing is wired, this 1 meg resistor coming from down under here is going up there. So I re-verified the assembly instructions, and this wire here is the one from the terminal strip, which comes from the 1 meg resistor, and it's showing going to pin 2 of the 5879. Well, that's not where it's going. It's going up to pin 2 of the 12AX7, so that's a wiring error, a bona fide wiring error, and it looks like it's always been that way. It's always such a treat to discover these assembly errors in Heathkit equipment, and from how grubby this meter was when I received it, it looked like it was somewhere where it got a lot of use. So apparently, having that wire coming from that resistor here going to a completely different place in the circuit, instead of going to ground, it's going to this node up here, which would be biasing this point really high. I don't know how it could have ever worked, but it seems like if it didn't work at all, they wouldn't have had it in a place where they were using it so much, where all the knurls on the knobs are so dirty. I really have no idea what was going on with that, but I think that's a bona fide screw-up. I verified that the wire should be going to here from reading the assembly instructions, so it's not a drafting error. So this matches this, and it matches the assembly instructions. So I got to move that wire. So far, that's the only mistake I found. Well, I've been cleaning this up. I tried to take the bulb out and the bulb shattered, so I've ordered some more number 47 bulbs. They usually come in packs of 10. And that's just as well. I've wrung out the circuitry according to the schematic and the parts assembly diagram, chassis assembly diagram, cross-checking the actual wiring with the diagrams with the schematic, and it all seems to be correct after I made that one repair, or changed wire rather, that was incorrectly connected. I've gone over this thing with alcohol soaked tech wipes and got most of the crud off, but there's still some various discoloration that just comes with age, and you know, the plating on the panels and stuff like that, it's always going to have some gunk. You're just kind of moving it around to some degree. I've cleaned the power cord as much as I can. I've taken the knobs and knurled banana connectors off, and I'm going to clean those. They have to be soaked a bit first. Clean the shields. Gone over again the whole chassis, top and bottom, every place I can get in without breaking something. So while I've got the covers off, that's the shields, that is. This is over the range switch. It's a particularly sensitive part of the circuit, pretty high impedance, so to minimize hum pickup primarily, it's shielded. And likewise, since it's connected into the 2-gang tuning capacitor, that's also in a shielded enclosure. Now this one here has an adjustment that can be made down inside that hole there, and that's a trim capacitor, and that needs to be accessed through a hole, which is kind of awkward to even contemplate getting at. Alright, so the shields are back on. I need to put some deoxit on the switches and pots. That'll be the next step. I do have the capacitors and the 1 resistor on order from DigiKey. Looks like Cornell Dubilier, or whatever their name is, came through. They had all the parts I wanted in appropriate capacities, voltages, and axial cans, except for the one that will replace this big 300 microfarad one. That'll be a radial lead one. I may try to salvage the can on this. I usually don't bother with that, but I might try on this one. If not, I'll just put a piece of perf board or something over the hole and put the new cap on that. I've done it that way before. I've also washed all the tubes, wiped them off with an alcohol wipe. Alright, I have the case shell down there, and also the handle, which I've removed just so the soapy water and the scrubbing can get underneath where the handle was. And I have all the knobs and the banana post and the 4 feet, which I've removed, also soaking in the same water but in a smaller cup. Okay, knobs and handle and binding posts are washed, and feet. Case has been washed. I'm just waiting for it to dry out. That wrinkle finish paint holds a lot of water down there. It's almost like it's porous, so it takes a while for that to dry. Now I have noticed now that it's cleaner that one side of this, yeah, this side is kind of bowed out. Not sure what happened to that. It looks like something was hitting it from the inside. It's kind of weird. I'm going to see what I can do to straighten that out a bit. I just whipped up a couple pieces of scrap wood to make a spacer with sort of an anvil, and then a piece of wood that I tapped on with my small hammer, and got it pretty well leveled out. Piece of wood got stuck on it. I may try to touch up that paint a little bit. It didn't have the chips before, but some of the chips came out while I was working on it. One thing I've learned about these Heathkit knobs that have the metal inserts, you really need to soak them in soapy water to get the gunk out of the grooves, the knurls, but you don't want to soak them too long because the adhesive that holds the aluminum insert in gets soft and dissolves in water. And if you leave it in too long, it'll actually start sort of seeping out around the edges, and you can wipe that up. You actually need to if you don't want it to, you know, show, but you don't want to do too much of that or the insert won't stay attached once it dries out. While I was at it, I added a fuse. I put a fuse holder on the bottom side of the chassis right next to the transformer and the terminal strip that handles the line cord. The cord can go either way. There's no designated hot or neutral. And normally that lead goes here directly to the wire going to the power switch. And I just took it off of there and put it on the fuse, brought it through the fuse, and then brought it back to this terminal so it can go on to the power switch. It's a 3/16 of an amp, or was that 0.187 amps slow blow 3AG fuse. Alright, I think it cleaned up pretty well. These two inserts, actually this one as well, but these two in particular are all scratched up. I don't know if somebody was playing around hitting them with a screwdriver or something, or if they had sharp fingernails, I don't know what, but I can't really do much about that. I don't think there's any good way I could buff those out without screwing up the concentric circle milling texture that's on those. I wish I could darken up the dB on there, but I probably wouldn't use it anyway. This is actually an instrument I might use, assuming it works well enough after restoration. If it lives up to its specifications, I can probably put it to use on occasion in my lab. Well, I decided to preserve the original can for that 330 microfarad cap. So I just removed every wire that was going to the plus side of it and mounted this little two-position terminal to one of the lugs that was holding the capacitor in place. The one of them is grounded, and that's exactly what the can of the big capacitor here was doing. It was tied to the chassis, so now the negative side of this cap is also tied to the chassis. Everything else is tied to this isolated or insulated. Isolated is better. I had to unsolder the end of this one and move the resistor over a little bit and kind of rebend the leads, and this one wire here wasn't long enough, so I had to extend it a bit. It's too much of a rat's nest down here to pull it out, so I just left that and put a little extension wire on here, but I think it came out all right. And there are those two. They're 22 microfarad. The original was 20 microfarad, 350 volt. It was that dual capacitor in a paper sleeve. Both of the negative leads go there, where the single negative lead of the other one went, and then each one of these I've just sweat soldered them onto the existing terminals because it's such a tightly wound mess down there. I wasn't sure I could really get it unsoldered very well. Now, this is something that doesn't happen very often. I got down to this particular part in the box of parts that came from DigiKey and had this rather large plastic Ziploc bag for such a small part that it should be. And inside was like a bundle of tissue paper and 2 layers of bags all wrapped up with tape, and I cut through all those layers and found, ta-da, this thing was inside the bag. I have no idea what this is. It's hollow, like, I don't think a wire oil would go through there. It's almost like something you'd find on a, mechanism, obviously, but not an electronic part in anything that I can recognize as such. Really no idea what this would be. That's a little window there. That's got a window. Interesting. The other side doesn't have a window. And there's that capacitor. This is actually larger than the original one. It's instead of 200 volts, it's 250 volts. I'm surprised that it's larger. Most modern parts are smaller. But it'll still clear the vacuum tube. I'm not too worried about it. I had to dismantle the whole meter, take it off there, because there isn't enough slack wire coming up through the hole in the chassis to flip this board around and get to the other side, or to the bottom for that matter, to redo the bottom capacitor connection. That was a pain. Okay, third time was the charm on this capacitor. The first time, as I already mentioned, DigiKey accidentally shipped a completely different part in place of this capacitor. Then they sent another order, but it got balled up somewhere in FedEx and it just got stuck in limbo and was not being delivered or moving through their system. So DigiKey sent yet another one, third time's the charm, and they sent it overnight. So I got it, ordered it yesterday afternoon, got it this morning. So finally I can put the last capacitor into this guy. Okay, that's in there. Hooked up exactly the way the original was. No insulation on the wires. Not really coming close to anything. On this side it's just going to ground, so if it's shorted out to anything here, it would just be where it's supposed to go anyway. And on that side it's going to the stub of the original lead, so I didn't have to unsolder that whole connection, which would have been a mess. Well, my ICO number 47 bulbs came in. Now hopefully it'll slip through this thing alright. It was a little stiff getting the old one out. And here's the original fiber, whatever it is, tube, sort of a light shield that goes around the bulb. Well, I can't get it to go through that grommet. I think the rubber has hardened up to the point where it's just not going to work without damaging the bulb going through. I even tried putting just a spot of oil on there, or silicone lubricant, and it still didn't want to go through. It's just a little too tight. So I think what I have to do here is get out the old 3D printer and make up something that'll work. I'm hoping that the plastic, the PLA plastic I use, is good for the kind of temperature that this bulb can be expecting to operate at. I'm not sure about that, actually. I'll have to look into it. Alright, I disconnected one of the leads from that lamp socket and just applied 6.3 volts DC to it, which isn't quite the same as getting it with 6.3 volts AC, but hopefully it's close enough. So I've let it go for about half an hour now. You know, it's warm, but it's not enough to burn me. I can hold on to it. So I don't know if my contactless thermometer will work on something like this. Let's see if I can. So I'm on the side of the housing there. I go over right about where the filament is to make sure I don't get off of it. Right about where the filament is. It's only reading like 70 degrees Fahrenheit. That seems too low. Let me try it on the metal, because that's actually where the plastic part would go if I 3D printed. It's only showing me about 71 degrees. Now it's a reflective surface, but I can't do much about that. I can go over here. At no point am I finding a temperature which is reading over about 70 degrees. And the glass temperature of PLA, in other words, the after printing temperature at which it starts having any kind of dimensional degradation from heat, is 140 degrees Fahrenheit. So even if I'm off on this somewhat, I think it's okay. And the part the part I'm going to print only goes up to here, so it's a long way away from the hot part. So I think the PLA printed part should be fine. Alright, I'm in Tinkercad. I'm starting out with a cylinder. I'm going to adjust its diameter to 18 millimeters. So 18 and 18, and make its height 3 millimeters. Alright, now that's for the shoulder, and I need to put the tube on top of that, but I need to put an open space in this first. So I'm going to drag an empty space cylinder and make it have a diameter of, yeah, that'll be 10.5. So 10.5 by 10.5, and its height will also be 3 millimeters. Now I just select both of those, and let's see, do an alignment. I'm going to align on the centers and make that a single object. So there's my ring. Now I got to drag another cylinder onto there. This one's just going to be for the shoulder, so that has a outer dimension of 12. And it's going to be 8 millimeters tall. And I have to put a tube through that, so I'll drag another empty space over, and that'll be the inner dimension, so that'll be 10.5 millimeters. I have the grid set to 0.5 millimeter increments. So 10.5, 0.5, and that has to be 8 millimeters as well. Double check my dimensions on that. That's the 12 millimeters. Yeah, so that's about right. So I'm going to grab these two, align them to be concentric, and group them. Now I think I screwed up on this guy. It has to have a hole in the middle of 10.5. Yeah, so I made the wrong diameter on that. It needs to be 18, so I have to ungroup that. Ungroup. And shift that middle one. Okay, that is 10.5. And this outer one is 18, so that's okay. Go back and group that. Now I just have to make both of these concentric. And then I have to raise this one up by the thickness of the shoulder. So I need to click this little up pointing arrow and make it raised by 3 millimeters. There. Does that look about right? If that's 3, that'll be about 3 to there, and another 3. Well, I did say I was going to make that 8 millimeters, right? And it is 8 millimeters, so it's not lying. And that one's 3. So I'm going to select both of these and group them. So now I've got the single object. And all I have to do is save that as the STL file. Then I have to make the mounting ring that'll go on the other side. Okay, I have a new workspace here. I've named the project IM-12 lamp holder ring. Gonna do pretty much like I did on the other one. I'm gonna drag a cylinder and a negative space cylinder. Okay, this guy needs to be again 18 millimeters. And it needs to be 3 millimeters tall. This guy needs to be the not the inner diameter this time, but the outer diameter, which is 12 millimeters. So this one's going to be 12, 12, and it's also going to be 3 thick. Make them concentric. Group them. Okay, so there's that one, and now I got to do is export it as an STL file, and that's done. Alright, I'm launching my Prusa Slicer application, and all I have to do is get my my 2 files over here, drag them onto the workspace. Okay, and I'm not going to mess with my presets at all. This is a quick and dirty project. I need to slice it, so let's do that. Okay, and now we can go through the different thicknesses, the different layers of the slice. Alright, now I got to export the G-code. Okay, design part's done. Should only be an 11-minute plot. Whoops, the line broke. Alright, with the filament reloaded, printing the skirt. I won't be able to see anything on this really because the print head will be in the way most of the time. Alright, there's the printed parts. I just have a little spider web of filament there. You just have to wait it to cool down a little bit, then I'll break those off of there and test fit it. Okay, there are the two parts. The ring does go on very firmly over the main part of the holder. And let's see if it fits the holder. Yes, it does, with almost no slop, but it slides on there easily enough. And it is just shy of the slots for the bayonet mounting, which is what I wanted. Let's see how it fits the hole in the particle, or the phenolic board there. That fits pretty well too. So let me snap this guy on there. Alright, it's on there. Get a little more light on this. I just used my small set of channel lock pliers to reach around and squeeze, and then slowly turned it while I squeezed it to the point where it fits tightly in there now. No rattling. Okay, with the lamp in the bayonet holder, I can just get it through the new lamp holder collar assembly, and now I can slip on the little light shield, which I've cut a little bit shorter. I don't think it needs to be as long as it was. And meanwhile, the little piece of red whatever that's supposed to be the color came off, so I need to glue that back on. And there it is. Seems to have come out pretty well. I don't think that area of the lamp holder will get even remotely warm enough to do any damage to that PLA printed plastic part. Alright, here's my first test after the restoration. I have to make sure that the sensitivity control is set to 100%, and the level control I'm going to set to minimum for the moment. The balance control to the center. The range switch should be set to any of the set level positions of the two that are here. I'm going to be putting in a 1 kilohertz signal, so it should be a set level that's near that. That'll be in the 200 to 2000 hertz range. So I'll put it in this set level position, then I can just go back and forth between them. I have the tuning control set down to 20. That's the lowest. The frequency on this is only showing going up to about 200. So I currently have it set to 1 kilohertz on my function generator. And that should be okay, even though the graduation here is only 200. It can test up to 20K. Well, just for the heck of it, I'm going to change the frequency down to 300 hertz. In 300 hertz, yes. So I have it connected up, or I will be connecting it up to the input terminals of the instrument, but I'm not going to do that till I powered it up and make sure there's no smoke coming out of it. So let's see, I have it plugged into my power bank over there. I'll turn it on here. There is a indication there, so I know the power's getting in. Let's Let's check the tubes. The 0A2 has got a shield around it, so I don't see a glow from it at this point. I'm not sure if I will. This guy's glowing. There's a glow on some of those other guys. A little bit down there. There's a glow on that one. So I think I've got a glow on everything that should have one. Alright, so I've got it to set level. I'm going to connect up the signal generator, turn the generator on, and adjust the level until I get some sort of indication. I'm not getting any indication, so that's not good. It's not getting past that first stage. Yep, have a little bit of debugging to do here. Well, this is interesting. When I just move the meter circuit board, I start getting a reading. I bet I forgot to tighten down the nuts on that. Okay, I've got a reading. Now let me see if I can get the level set. And I can. Very good. So that's working. I've got it set to 100%. Now I'll set the range switch to the appropriate test frequency. Since I'm at 300 Hertz, I'm going to set it up to the 200 to 2000 range. And I get a drop in the meter. At this point, I really do need to adjust that knob a little bit. It's a little bit askew. So the tuning I should adjust for minimum reading. So I am getting it cranking downwind here, so the notch filter is working. Got a couple of iffy spots in it. So there's where the notch is. Okay, so I've got it pretty well nulled out. It obviously has a bad spot on the pot. I need to adjust the balance for the minimum reading. It also has some iffy spots in it, but I'm not really getting it to go any lower, so I'll leave it where it is. Now I have to change the sensitivity clockwise one position, so it goes to 30% sensitivity. I should see a rise in the meter movement, and I do. I should go to another one, and once again I'll adjust the tuning for a minimum. Once again, tweak the balance. It's about where it is. Increase the sensitivity again. Adjust the tuning for the minimum. It's really sensitive at this point. I'm going to back it off one position. So that's about where it is. Tweak the balance a little bit. It's about where it is. So I should be able to read the harmonic distortion according to the range or the sensitivity, which is currently on 3%. So I have to read the 3 scale, and I'm reading about 0.4 0.4% distortion. Which, you know, I'm not sure if that's accurate or not because I don't have anything else to check it with. I also noticed that this pot has, or this indicator has not come up to the point where I thought it should. I wonder if this is it should be within the range here, so this should represent 200 and this should represent 20,000 or 2,000. So yeah, I'm setting at 300 Hertz. It is reading a little bit high, but it's in the ballpark anyway. So I've got a reading, some kind of functionality on this. The signal's making its way through the circuit for sure, and it's the notch filter's working and the meter circuit's working, so basically all the components are functional, with all the resistors being measured and verified and all the capacitors replaced with fresh ones. I know there's not a problem there. There may be some iffiness in the switch selection, certainly in some of these wire wound potentiometers, but I think it's basically working. Now, one thing I can do is change the waveform on the signal generator. I can go to a ramp wave, which will add some higher harmonics, thereby more distortion. Oh yeah, bang. That's a lot of distortion. Square wave, be even higher. Yeah, that's a lot. Go back to sine wave, and I get my low indication. One thing that I should be able to do to add some distortion into this is to add a couple of inverse parallel diodes in the signal path, so it doesn't start conducting until some ways into the sine wave. That should give me some fast rising edges and therefore some harmonics. Okay, in that high sensitivity, where it can only read up to 3% distortion, I have to back it off because there's already more than that. So right now I'm in the times, or the 10% range. Therefore I'm on this scale, so I'm now up to 7.5% harmonic distortion. So it responded the way I thought it should. Let's go back and change this to the ramp again. It's obviously, now that I'm in the 10% range, I'm getting a more reasonable reading. So 10%, I'm getting about 8.5% harmonic distortion. I'm too lazy to check and see if that's a reasonable amount for a ramp waveform or not. What if I go to a square wave? I'm sure it'll be just chock full of distortion. So bang, yep. Take it down to 30%, that's too much. 100%. Yeah, so we're up to 50% harmonic distortion, which doesn't sound unreasonable to me. I'm certainly getting readings here that are in line with what I expect, so I'm happy with that. Alright, I've gone through the calibration procedure. I've reconnected my signal generator. I've got it set to 5 kilohertz sine wave, 2 volts peak to peak. I have it on set level here. Balance is centered. Sensitivity is 100%. I'm adjust tuning for, or I'm still doing set level, so I need to set the level control here for 100%, which I've got. And now I have to put it in the 2,000 to 20,000 range and adjust the tuning control for the that's about where it is. Increase the sensitivity, try to null it out some more, play with the balance to see if that improves it any. Go to 10%. Yeah, that's too high, so back to 30%. Okay, This is pointing a little bit high, like I knew it would. I need to adjust it so it's pointing a little more accurately. It's not as low a reading as I would have expected for a sine wave. It should be much lower distortion. But if I take it down to 100% here, it's pretty close. Alright, there's the beauty shot. Alright, let's take a look at the manual. This is a full manual in reproduction form by manualman.com. So it starts out with the usual resistor and capacitor color codes, which were common at that time on capacitors, not used much that way anymore. So you have the usual picture of the instrument, the specifications. It can be used on frequencies from 20 cycles to 20,000 cycles. That would be hertz to us in 3 ranges. Distortion ranges 0 to 1, or 0 to -1, -3, -10, -30. That's dash. So 0 to 1. Distortion is 0 to 1%, 0 to 3%, 0 to 10%, 0 to 30%, 0 to 100% of full scale. As a voltmeter, it can be used 0 to 1, 0 to 3, 0 to 10, 0 to 30 volts full scale. Input resistance 300K. Minimum input voltage for distortion measurement 0.3 volts. Output voltage for monitoring 2.5 volts at full scale meter reading. The meter, both in voltmeter and distortion modes, is good for plus or minus 5% of full scale. It weighs 11 pounds and is 13 inches wide, 8.5 inches high, 7 inches deep. Introduction. This Heathkit is the result of many years of engineering effort to reduce the costly and complex devices heretofore used for harmonic distortion measurements to the simple and easy to construct level so traditional in Heathkits, without sacrificing the necessary accuracy, stability, and operating convenience. The detailed instructions in this manual were specifically written with your problems in mind. We suggest that you take a few minutes now before starting any construction and read the entire manual. In this way you will obtain a rough idea of the assembly process. The large fold-in pictorial diagrams are for your convenience and are quite helpful if attached to the wall above your workspace. The diagrams are repeated in smaller form within the manual proper. We suggest that you retain the manual in your files for future reference, blah blah blah. Notes about unpacking the kit, and then it starts out right away. It doesn't start out with a parts inventory. It goes straight to mounting the parts. So this is the older perfunctory style of Heathkit manual. Still better than what most of the other kit companies offered, but nothing like what they were famous for later. You really are just kicked straight in with good diagrams, but not as many as they would have used later, and the assembly steps are certainly more terse and really just required more wherewithal on the part of the kit builder. So we start with the sockets and other things, rubber grommets, terminal lugs, the wire wound potentiometers that are chassis mounted, some of the shielding for the tuning control, a bunch of other stuff, mounting the tuning condenser. And there is sort of a diagram of what you're supposed to have assembled up to this point. Details on mounting the banana binding posts. The wiring starts out by wiring up all the parallel tube filaments and the pilot light, and the one potentiometer on the back panel. So it's just like this first one. Twist the 2 red leads from the transformer and connect one lead to pin 1. S means solder that once you put the wire on it. and the other lead to pin 6S on the 6x6 or 6x4 sockets refer to pictorial 2, which is like, where's that? Pictorial 2. Oh, there. Well, that's figure 2. Can't be confused with pictorial 2, which is on the next page and turned sideways. Okay, so it goes on from there. This is pretty much the bulk of the wiring right here in this one very cluttered diagram, but it is possible to follow the connections. They got the angles right and positioned components to not block other things. Still, it's not like what they had later on that would have made this cleaner. On the other hand, a lot of the older or the more modern kits in their product line had circuit boards, and you didn't have nearly so much point-to-point wiring. So it goes on, and you have some details for like wiring up the sensitivity switch, or I'm sorry, this would be the range switch, which is actually mostly assembled in another diagram. A lot more of the same stuff. Some details on wiring the power switch in the back of the meter assembly. And there's more on the meter assembly. There's the range switch in its pre-assembly, which you had to do before doing these things a couple pages earlier. So again, just a lot of very terse messages like that. A detail on the panel bushing for the knob that's used as a pointer for tuning, and the extension shaft and the insulated shaft coupling and the drive pulley, all that stuff, and then another view of that from the rear, and lacing up the pulley cord. More details of assembly of the range switch. A diagram that was previously presented is presented again here. Preparing a shielded cable, the one and only in this kit. Preparing the strain relief for the power cord. This identifies where the various calibration controls are. A trim capacitor through a hole in the shield, and a pot from the rear, 2 pots up here on the chassis, the rubber mounting feet on the case. Then we get into test and calibration. Circuit description. A small view of the schematic in addition to the large fold-out one. Diagram showing a typical way you'd use this with other equipment. Example of a test procedure. And a rear view of the chassis. A bibliography of other things you might want to read to learn more about this type of thing. Then information on how to use the technical consultation department, the factory service facilities, the local Heathkit centers, how to get replacement parts, how to ship things back to Heathkit if you need to, the warranty, and now the parts list is in the back. And then a replacement parts price list. Not everything in the parts list is included here. And then the big fold-out schematic, which may have been a loose sheet in the original manual, but here is bound. I made a copy of this before binding it myself. I always order my manuals without the binding because they use plastic comb binding, and I prefer to use wire comb binding. And also to use bigger diameter winding than they might want to use on their own because it makes the pages turn easier. So when I received this, I just made a copy to have loose, but there's this one that's bound in the manual. And then Manual Man even reproduces things like the replacement parts ordering forms. And then a typical component types schematic to physical appearance chart. And then the back of the manual. Alright, here's the full-size schematic diagram for the IM-12. It is slightly scrunched from left to right. I think the original was a bit wider. Manual Man does do that sometimes if by doing so they can fit it on a normal piece of 11 by 17 paper. But they won't go to the point of being ridiculous about it. If they have to go wider, then they just print it on a couple of sheets of paper and tile it together with tape. Anyway, so that's why the tubes look slightly ovaloid, because they've been scrunched ever slightly in the horizontal direction. Parts of this schematic are fairly clear, but other parts are pretty hard to follow, particularly the sensitivity switch, and the range switch isn't the easiest thing to figure out either. So what I've done is, during my usual circuit study, I prepared my own schematic. Just a sketch, but it has more details, it's arranged differently, it's spaced out a little better, has a lot of little notes that I wrote to myself, but I'm going to use this to go through the schematic and the circuit theory. So what's the purpose of this harmonic distortion meter anyway? Well, it's really used almost exclusively with testing audio equipment for fidelity, and the way that's done is to pass a signal through it from an externally generated piece of equipment, like a signal generator or a function generator, to pass a pure sine wave through, which I've drawn poorly here, and that goes into the piece of audio equipment you're testing. Could be like the inputs of an amplifier, and then you come out of the speaker outputs or the headphone output or whatever, or it could go through some other piece of audio processing gear and then come into the input of this harmonic distortion meter. The whole idea is that if you have high fidelity, perfectly high fidelity in the piece of equipment being tested, a sine wave coming in will come out unmolested. It will be exactly the same shape, not necessarily the same amplitude, because that could change, but the same exact shape. And a sine wave is not just any old shape that goes up and comes down and comes back. It has a specific mathematical curve to it. And once you've seen a true sine wave, you kind of remember the shape, and you can pretty easily tell when you're looking at a sine wave which is not sinusoidal, because there's just a particular look to the curve that is pretty easy to recognize and discern from others. Anyway, so the idea of a sine wave is that it has no harmonics to it except for its own. And what is the harmonic? Well, if you have a waveform like this and it has no harmonics, then it is just that wave, and there's no other component of a wave inside of it. But if you start adding a little distortion, maybe the curve is shaped a little different here, or this line, instead of being slightly curved, is really straight, or anything like that. Or if you take, for example, a different kind of waveform, like a ramp waveform or a sawtooth waveform or some sort of a square wave, these all have additional harmonics besides their basic fundamental frequency, and the harmonics go up. So let's say that this is a 60 hertz sine wave. Then there would be harmonics that are higher in frequency than that, but only if it's not a pure sine wave. Now, a triangle wave like this will have a bunch of harmonics, and you can characterize it because of the types of harmonics and how big they are and where they are in the possible places where harmonics might be. If you have a waveform like this, it has even more harmonics. Basically, anytime you have a more abrupt change in the waveform, that indicates that you have more harmonics, and especially higher harmonics. Square wave is just chock full of harmonics because anytime it's changing shape, it's doing it vertically. So that is just chock full of high harmonics. If you add all the harmonics together, well, I should go back. Let's say that we have a chart of, here's a timeline, and let's say that this is your 60 hertz signal. Oops, I meant to just draw a straight line there. I'm terrible at this. It's a straight line. This is 60 hertz. Now let's say it has a harmonic out here at some frequency that's higher than it. And maybe it goes up about that high. And maybe there is another harmonic here that goes up about that high, and so on. Different harmonics, and they don't all have to be descending. You might have, you know, one up higher again, but various harmonics. And those, if you add them together at any given point along the waveform, if you take what those other waveforms are doing at that same exact moment as the fundamental waveform, and you add them all together, and then replot that, you'll see the actual shape of the waveform. So maybe, you know, all this added together ends up plotting this shape, or this shape, or that shape. If you are passing a sine wave, a pure sine wave, through a piece of audio equipment, and if it's not distorting, then you will get a pure sine wave out of it. But if the resulting output has any harmonics in it, that means that there's some distortion that has happened because the waveform has changed somewhat from being a pure sinusoid. You know, if it's just a couple of harmonics and they're really low amplitude, probably you'd never know or care. But if you have a lot more harmonics, you know, a waveform like this or this or this sounds very different from a waveform like this. So the more harmonics you have in the waveform, especially if they're at higher amplitudes, affects the quality of the sound and the accuracy of the sound. So that's why people use harmonic distortion analyzers or meters, is to determine if a piece of equipment is corrupting the sine wave coming through. And if it is, then you know that it has issues and should be improved. Now, in reality, most music is chock full of harmonics because very little music has actually got sine waves in it. You know, an instrument like a flute or an organ pipe might be the closest to a sine wave, but even those have harmonics in it. It's the harmonics that make the different instruments sound like different instruments, for example. How you can tell a saxophone from a flute, for example, or a clarinet. It's all in what kind of harmonics are in the waveforms of their sound, and how high are they, and what order, and spacing, and everything like that. So how does this meter work to detect if there are corruptions, in other words, distortion, harmonic distortion, that is, in the waveform? Well, the easiest way is to remember that if it's a pure sine wave, there's only the one harmonic, and it's the first harmonic, or the fundamental. And if you apply a filter to the waveform that's coming into the meter, and you filter it so the only thing that's allowed through is a 60 hertz, again, assuming this is a 60 hertz signal. If you filter it so only a 60 hertz signal is allowed through, then all you would hear is the harmonics, or all you would measure is the harmonics. So there are several ways of doing this, but the way the majority of them, at least this type of meter and most of the competing ones at the time, was to make a filter that subtracts the fundamental and leaves everything else, and then just measures that other stuff and compares it to the amplitude of the original waveform and says, well, this is a percentage of that, and that's your total harmonic distortion, or THD. And probably most of these devices of this type use what's called a Wien bridge notch filter. It's a fairly simple circuit, and you can tune it so that, you know, here's the amplitude of a signal, but as it gets closer to that defined frequency, it starts notching down, lowering and lowering until it's brought to 0. And then as you get higher above that frequency, the amplitude comes back up, so it's no longer being attenuated by the filter. If you do nothing else, the characteristic profile is more like this. It's a gradual slope down and a gradual slope back up on either side of the notch, the part that's being filtered out. But if you apply feedback from the output of the notch filter to the input of the amplifier circuit that's driving it, you can cause it to have a much more abrupt shape to it. So it's full amplitude up to fairly close to the desired frequency, and then regains full amplitude fairly close to that as the frequency goes up. So this is without feedback, this is with feedback. And the idea being that, for the most part, because harmonics, the next available harmonic is usually not right next to the fundamental, it's some distance off, higher, and therefore, let's say there's a harmonic here. Well, by that point, the notch is already passed, so it's showing you the full strength of the harmonic if it's over in this area. So you want to make this as abrupt as possible, as narrow as possible, so that it does not attenuate the other harmonics that are up above here in frequency. Alright, well, this circuit is a tube circuit, and as such, it has tubes in it. They are not all vacuum tubes, however. One of them is masquerading as a vacuum tube, but the others are all vacuum tubes, and they run by thermionic emission, that principle of operation. So let's start out with the power supply. You have a ungrounded power cord. This particular instrument's only 120 volts AC. There's no double primary winding to allow it to operate at 220 or 240 volts AC. Heathkit equipment that was older, they didn't bother with fuses on the power line side. I have added one here, but originally it was just coming in through the power switch, through the primary winding, and back out. Now you have two secondary windings, because there's vacuum tubes and they're all using a 6.3 volt filament. We come out with just a simple winding, and then everything that needs that is across it. There's a single filament for the 6X4, a dual filament for the 12AT7, another dual filament for the 12BY7, another dual for the 12AX7, and a single filament for the 5879. There's also, and I haven't sketched it in here, the pilot lamp for the front panel that tells you the power's on. And then finally, a wire-wound potentiometer. That's 100 ohms. And the center of that is grounded. And that is a way to couple a certain amount of the AC waveform, low voltage, to ground. And that's actually beneficial in canceling out any hum from the power line that's picked up by other parts of the instrument. You can kind of buck the signal out and cancel the hum for the most part by careful adjusting of this pot. Now for the other secondary winding, and this is the one that provides the working voltage for the circuit. It's a center tapped winding, 210 volts, that should be RMS between the outer legs of the winding and then the center tap in the middle. There's a 6X4, and that's a dual diode or dual rectifier tube. So it has the plates and the cathode which is like the anode and the cathode of a silicon diode. So this side of the winding goes through one of the diodes to the cathode. This other side of the winding goes to the other diode to the cathode. And it's got the common cathode. It's really just the same as this if done with more modern diodes. Immediately there's a pi filter, so two capacitors with a resistor in between them that filters out most of the ripple resulting from the rectified AC waveform. And then that's passed into a 0A2 vacuum, or again, this isn't a vacuum tube. This it has a filament, but this one does not have a filament. The 0A2 is a gas-filled tube and does not have a filament. It does not operate by thermionic discharge, or emission rather. It just has a simple plate, and I'll call it the cathode here, but it isn't really. It's just like a giant neon bulb. It only has two electrical terminals, but on this particular model of tube, it has two pins which are internally connected together to the plate, and two more pins that are internally connected to this point inside the tube. So they chose not to put an external jumper between these or between these. This dot denotes that it's a gas-filled tube. And the particular characteristics of this 0A2 tube is that it acts as a voltage regulator and tries to hold the voltage from here to here at approximately 150 volts. It's quite stable, although it's not necessarily accurate. Pretty much any circuit where you need accuracy with this, you have the stability of the tube, and then you do something, usually afterwards, to dial it into the exact voltage you want. So you get stability with external accuracy. But on this circuit, it's not critical exactly what the voltage is, but it needs to be regulated so you have a nice, smooth, even voltage. This removes any remaining ripple. And then finally, we have an additional RC filter, just for good measure. And this one is a much larger capacitance, 300 microfarads instead of the 20 microfarads for these guys. And this is the point where there's two grounds in this meter, the chassis ground and the wired circuit ground. This symbol is used for the wired circuit ground. This is used for the chassis ground. For reducing noise pickup, mostly from the power line, this instrument isn't that susceptible to RF interference because it's not designed for anything except the fairly low frequency range of 20 to 20,000 hertz. So it's mostly concerned with lower frequencies like from the power line. And they determined that using the wired ground was a better way of going for that reason than using a chassis ground. But still, the chassis needs to be grounded, and this is the common point at the negative side of this large filter capacitor. There's only a couple of exceptions to this where the ground and a part of the circuit's taken from the chassis instead of from the wired connection. And the final output of this circuit, which is about 150 volts, is produced here and is called A in the circuit power supply A. So the instrument starts out with an amplifier. Just because you don't know what the input amplitude is, you want to get it up to a certain optimal level for the circuit to work properly, everything downstream. So here are the input terminals, the input plus and the input minus. The input minus is connected to the wired ground, and then the positive side is taken off and used downstream in this circuit. I'll get to that later. But basically we just have a potentiometer. It's the only carbon potentiometer in this entire circuit. All the other ones are wire wound types. This is 500K, and by moving the wiper up and down you can go from full attenuation to no attenuation, so you have a wide span of voltage adjustability here. To remove any DC component of the circuit, there's a series coupling capacitor, and its value is selected to have no attenuation of the signal in the desired 20 to 20,000 hertz frequency range. Then this is all done right up on the front panel. Then we get down to the chassis through a length of shielded cable, and its shield is connected to the chassis rather than to the wired ground. Of course, it's electrically the same, but they figured out which is the best way to do it for minimum noise pickup in the circuit. And then we have a resistor reference to ground. In this case, again, it's the chassis ground. And this is needed when you have a series capacitor to reduce or remove the DC component of a signal. You need to then ground reference the output. And what that means is, let's say you had a signal, but ground is like here. Or here's where ground is, and the whole signal is up here above ground or below ground. That's not desirable when you're trying to do measurements. So running it through the capacitor and then ground referencing the output of the capacitor snaps it back to have the AC signal half above ground and half below ground. So once we've attenuated the signal, we need to boost it back up to a known level, and that's done with this simple triode amplifier. In this case, it's half of a dual triode tube. So it's the 12AX7 tube, a very classic triode. Half of it's used here, and the other half is way over here at the other end of the circuit. It's a classic configuration. So you have power supply A up here, again about 150 volts above ground. There's a resistor going to the plate of the triode. The cathode of the triode goes down here with a resistor to ground. In this case, it's using some of the same resistance that's used for ground referencing the output of the DC coupling capacitor, or AC coupling capacitor. We're trying to couple AC, not DC. And then the incoming signal is applied to the grid of the tube. So as you modulate the grid, the voltage down here also modulates, but at a higher level. So it's your classic voltage amplification tube circuit. Doing it this way, instead of giving it its own resistor to ground, for example, allows feedback. And feedback's always important for good amplifier performance. But this isn't the actual output of the circuit, although it can be used as a kind of output. The normal output of the circuit of this type is up here at the plate. So that comes through here, and it's capacitively coupled again. And again with a resistance making its way down to ground, wired ground in this case. It does the same thing as it did here. If any DC offset or DC component was introduced in this amplifier, it's stripped out by this. Now this is a pentode tube, but you'll notice that one of the grids is connected to the cathode, another grid is connected to the plate, and only the one grid is driven from the input. Different people who are into tubes, and I'm not really into tube theory very much. I'm much more of a solid state guy. But Heathkit identifies this as a triode connected pentode. So they're trying to operate it as a triode even though it's a pentode. And this is a 12BY7 tube, by the way. I don't know if there are advantages to making a triode circuit out of a pentode, or if they just did that because they had a lot of 12BY7s laying around they were trying to use up. I don't know. Maybe some more tube savvy person can weigh in the comments. Again, the cathode is referenced to the middle of this voltage divider that goes from the input to ground. And I should mention that by controlling the current through here, you can control characteristics of the way this particular amplifier is working. there's a balance potentiometer connected as a rheostat, so it's not actually being used as a voltage divider, it's just being used as a series adjustable resistor. And then that goes, this is on the front panel, then it goes through another series adjustable resistor, in other words a rheostat, to ground, and this one is internally adjustable and it's used during calibration. So it's the coarse balance control. This is something that's adjusted every time you take a measurement to make sure that you're introducing as little, I'll just call it corruption here to keep it simple, into the circuit before you actually start taking the measurement. So it's dialed out on the meter by using this balance control. Connecting this tube the way it is with the cathode of this preamplifier going up here and connecting to the plate of this tube, and then the plate of this tube being connected to the grid of this tube, that results in this particular amplifier generating two outputs which are completely out of phase with each other, so 180 degrees out of phase. And all that means is that while one output has a sine wave like that, the other output's waveform is just a mirror image of it, flipped over the other way, 180 degrees out of phase. And that's done because the next part of the circuit is the half Wien bridge notch filter. A normal Wien bridge is drawn like this usually. A signal is applied to this point and this point. You've got two resistors in these two legs, and a resistor and a capacitor in series in this leg, and a resistor and capacitor in parallel in this leg. These resistors are the same value and these capacitors are the same value. Then you take the output from here and here. So you're measuring between these 2 points. And this takes into account and uses the capacitive reactance along with the resistance. This side of the bridge is just resistance, so it's not affected by frequency, while this side is affected by frequency. And because in this sense, on this side, the capacitor is in series with the resistance, and on this side it's in parallel. Anyway, so you get different effects in these two legs due to the capacitive reactance. And then if you compare that to this side, which is not affected by the capacitive reactance, and you measure the voltage across there, you can see a change according to frequency. So that would be a Wien bridge filter. And a Wien bridge filter is part of a Wien bridge oscillator, which is a type of sine wave generating circuit. Normally the entire bridge is used for measuring a frequency, and again, it depends on the changing capacitive reactance. But what if instead of these two capacitors being the same, what if they're opposing values, for example? What if this resistor, or what if this capacitor gets smaller while this one gets larger, or vice versa? You can see there's some dynamic things that can go on. And that can change the characteristics of this point here according to frequency. And indeed, because this one's in parallel and this one's in series, the overall effect you get is that one of them is more effective while the frequency is going down, the other one's more effective while it's going up. And then if you take this part of the circuit out and make a half bridge out of it, you essentially get rid of this, and you just measure from this point to ground or whatever. Now you'll find that the signal is really reduced a lot at a particular frequency, but not so much on either side of it. And you can change what that frequency is by increasing one of those and decreasing the other, or vice versa. So it's essentially notching out a particular frequency and then letting the other frequencies by more or less unmolested. But you need to drive this differentially, so you want the drive on here to be opposite this one, and that's what's happening in the circuit here. I know I kind of made a muddle of it. I hadn't really thought too carefully about how I was going to explain that, and I probably put my foot in it a little bit, but I think you'd still get the general idea. So we come up with this amplifier here, which its job isn't so much amplifying the voltage as it is making a copy of the preamplification voltage and making sure that there's a equal and opposite phase coming out of the two output signals. Now, they actually aren't the same voltage because the resistor values here and some other factors, one of these voltages is about twice what the other one is, but they are the same shape and they are 180 degrees out of phase. Now, this may look like a lot of garbage. You have a switch that selects between three resistors, and then you have an adjustable capacitor. Ignore the trimmer capacitor, it's across it, pretend that's not there. Just pretend it's this guy. And then on this side, you have, again, one of three resistors, or a short circuit, so like a resistor with 0 ohms, in two positions. And that is connected not in series with a capacitor here, but in parallel, because one side of the switch goes to one side of this adjustable capacitor, and the other side goes back to here. So that's where we get the equivalent series and parallel resistances. This resistor in series with this adjustable capacitor, this resistor in parallel with this adjustable capacitor. Both these capacitors have the same maximum value, but their value changes oppositely at the same time because they're ganged together mechanically. There's also another one of these RC deals with a capacitor coming out of this output and then a resistance to ground. The upshot is that this part here is like this part of the circuit here, with the capacitors being adjustable. Just to make it work a little better, there's a small fixed capacitor across this one and an adjustable small value, just 5 to 20 picofarads across this one. This one's 4.7 picofarads fixed. But that's all that is. It's just a way to adjust that Veen bridge or half Veen bridge circuit with that big adjustable tuning capacitor, which is adjusted from the front panel and is called tuning. Now, there's a subtlety here. There are three ranges on this range switch. One is 2 to 200 hertz, or one is 20 to 200 hertz, the next one is 200 hertz to 2000 hertz, and the third one is 2000 hertz to 20,000 hertz. So those are your three ranges for this filter, and the positions in between do nothing. Now this is the side that has the resistor in series with the capacitor. So if you have the switch in one of those three positions, it is a resistor in series with a capacitor. But if you have it to the intermediate two positions, either of those, now you don't have a connection, and it's like this whole part of the bridge has been removed electrically. So what you have there now is this output of the tube isn't going anywhere, and it's just this output of the tube through this capacitor that is now going through this resistor in parallel with a capacitor and then out. It changes it just into a simple parallel resistor capacitor circuit, and the signal moves on without being tuned. At the same time, when you have that, well, you might say, hey, but if you're running a signal through something with capacitance in it, it's going to change the signal, and that's right. However, in those same two positions, this side of the switch shorts out the resistor, and because the resistor and capacitor are in parallel, it shorts out the capacitor too. So when you have this range switch in either of the two positions that are called set level, this part of the circuit is taken out completely, and this part of the circuit is short-circuited. So it's really like just taking a wire from this AC coupling capacitor and jumping over the entire null circuit and going out, so the signal does not change at all. But as soon as you get it into one of the other three positions, the series RC circuit and the parallel RC circuit are reinstated, and they have the notch filter effect on the output signal here. Well, because we've gone through all that filtering, and even at frequencies where it shouldn't be doing much filtering, there's still some attenuation going on, so you need to boost the signal back up again. And so here's another pentode connected as a triode. I think that's what's going on. Let's see, the upper grid is connected to, well, the upper grid is just connected to ground. The middle grid is connected to a voltage off the tube voltage supply, the 150 supply, with a filter cap to ground. So this grid is held at a constant voltage near the power supply, and this grid is completely grounded, and the signal from the notch filter goes into the remaining grid, and the cathode goes through a resistor to ground. But it's still acting as a voltage amplifier, and as such, we're taking the output off of the plate. So this point wobbles up and down at a higher voltage than whatever was coming in over here. And then finally, we run it through one additional stage, but it's a buffer, not an amplifier. This is the other half of the 12AX7 that was way over here as the preamplifier. In this case, its plate is just connected directly to the 150 volt power supply. Its cathode is just going through a resistor to this point, but it is not going to ground. Well, you might think that this should have some sort of a ground reference on it, and it does, because that's really connected back here to this point in the circuit, and there is a resistor from that point to ground. So this amplifier has its cathode referenced to ground through this resistor, and this amplifier has its cathode going through a resistor, in this case 47K as opposed to 4.7K over here, and it's really connected to this same point. So it's like the other cathode is just through a resistor to this same point, and they both are referenced to ground here. This signal wobbling around, the output is taken from this point in the circuit. If you took it here, it would just be the power supply and it wouldn't wobble around. You have to take it from the cathode in this instance. But in this instance, it's being used as the output of this amplifier stage, and it's also being fed back to here. And that is a negative feedback arrangement, so it stabilizes the operation of the amplifier. And most importantly, this is what I talked about earlier, the feedback from the very beginning or the very end of the filter circuit to the very beginning of the filter circuit sharpens the curve on the notch, so it makes it a narrower, tighter notch with steeper slope, so it's more selective of which frequency it's filtering out, and doesn't tend to disrupt or attenuate any frequencies that are not really close to that tuned frequency. So that's how all that works. So, assuming that you've got the range switch selected to one of the frequency ranges instead of to the set level, what comes out of here should not have the fundamental in it anymore. It should just have the harmonics that were not filtered out. And once again, those are coupled through a capacitor. And normally, that goes through a switch and then goes through all these resistors back to ground, so it is ground referenced. And everything from this point on is essentially a vacuum tube voltmeter of a sort. It's not differential like most of those are, but it's still a vacuum tube voltmeter. Normally, we would use this meter circuit to measure the amount of harmonics there are, hence the amount of distortion amplitude there is. The sensitivity switch has 3 gangs to it. One of them is just a simple selector with 9 positions, and the other 2 gangs are set up to act as simple switches, where if you're in 4 of the positions of this switch are for having the meter measure voltage, and 5 of the positions are for having the meter measure the percentage of output here versus the amplitude of the original incoming sine wave signal. So that's how you can get it to read a percentage instead of just a raw voltage level. But let's say we're in the percentage mode, so the gangs of this sensitivity switch in percentage, in any of the percentage ranges, this switch will be closed, thereby connecting the output of this amplifier up to the top of this big resistor voltage divider and then back to ground. Meanwhile, the original signal before all of this, and thus not molested or altered in any way by all this circuitry, comes straight off the input terminals, and it goes to a voltage divider with a 1 meg resistor up here and a 150 ohm or 150k resistor going to ground. So it's the voltage divider, and this point here is the result of that voltage division. Well, if you're in the percent mode by the selection of the sensitivity switch, this point is dragged to ground through this switch. So it's not used and it's just grounded. But back to the situation where we're in the percent mode of the switch, the signal here does go through. It's applied to this big voltage divider to ground, so you can tap off with the no attenuation, some attenuation, more attenuation, more attenuation, and more attenuation coming down. And it's a 683 versus 216 ratio. This one is 683.8K, the next one is 216.2K, and then the next one's an order of magnitude over, so 63.38K instead of 683.8K. The next one's 21.62K instead of the 216.2K. And then finally there's just a 1K resistor on the bottom of the divider. So we don't take it down by orders of magnitude directly. It's every 2 positions is an order of magnitude. Then we have the switch over here, and if we're in the 1% position of the switch, we're just taking the output of this switch from the unattenuated signal coming from the output of this amplifier. If you're in the 3% position, you're getting it from this point in the attenuator. The 10% position takes it from the next position down. The 30% takes it from the next position down. And the 100% takes it from the final position down in the divider. So that's how that works for the 5 harmonic distortion percentage positions of the sensitivity switch. On the other hand, if you want to use this as a voltmeter to measure just the amplitude of the incoming signal, then you put the sensitivity switch in one of the 4 voltage measuring positions. Those are these here, which are 1 volt, 3 volts, 10 volts, and 30 volts. And we have to adjust what we're doing with the signals coming into it. So now we have that input signal which has just been brought around all the amplifiers, and it's been voltage divided here, and this switch is no longer closed because that's the percentage mode switch. So now this voltage divider can do its job, and we're in voltage mode now, so this switch closes and connects that input signal to the voltage divider. And once again, it divides down by 1, 3, 10, 30 kind of jumps, and are connected directly to those 4 positions of the switch. Meanwhile, we take the output that we're not using from all this circuitry here, the notch filter circuit, and we're connecting it to ground through this part of the voltage switch. So it's tied to ground and it's not doing anything in the circuit. So finally, when we come out of the sensitivity switch with all of its range adjusting or sensitivity adjusting positions, whether we're measuring the incoming voltage or the percentage distortion voltage coming out of this circuit, it needs to be reamplified again. So we come through yet another AC coupling capacitor and essentially a 10 meg resistor going to ground, but there's this additional calibrate control, which is another wire wound rheostat between this point and circuit ground, in this case chassis ground. So it's nominally a 10 meg resistor, but you can tweak it a little bit with this calibrate control. So here is half of the 12AT7 triode tube and the other half of the 12AT7 triode tube. Again, we're connected with the A power supply, 150 volts, through a resistor to the plate. The grid is controlled by that AC coupled signal, and the plate or the cathode is connected to ground through this resistor here. Now, when I said before that this whole thing was an adjustable ground reference resistor, that oversimplified it a little bit, because this is the primary ground reference resistor. This is the resistor that's common to both that and the cathode, and its adjustability is more pertinent to the cathode functionality than it is to the ground referencing function of this resistor. So it's really to adjust this amplifier stage here. And just like with the other amp up here, we can also introduce a negative feedback to this point from a point downstream in the circuit. So there is that feedback signal that's brought into this point. We take the output from the plate of this first tube. Once again, we have an interstitial AC coupling with a 10 meg reference, this time directly to ground. It's the chassis ground in this instance. And then another identical amplifier stage, except this one has a different resistor value from the power supply. And in this instance, the cathode is tied directly to ground. It does not have a resistor. So where have we seen that type of thing before? Well, we haven't got an exact duplicate of it here, but it's acting somewhat as a follower circuit. So it's more of a buffer than an amplifier here. This is doing the bulk of the amplification. So it's our post-notch filtering amplifier. It's also the power amplifier for the output of the device. And it goes through a final coupling capacitor, but no resistor this time. We're counting on the resistance of whatever you hook up out here on the output terminals to ground reference it. And if for some reason you didn't want it ground referenced, we're not going to force it to be ground referenced here. That's up to whatever you hook up. But the minus terminal is ground, and the plus terminal comes from the capacitor. And this is really for use by an oscilloscope, because it allows you to see what the waveform is that you're working on. If you have the sensitivity switcher selected to voltage mode, you're just going to be seeing the sensitivity adjusted wave shape of the raw input signal, and you'll be able to see that wave shape on the scope. On the other hand, if you're in harmonic distortion percent measurement mode, you're going to see the shape of the signals that are the harmonics, which were not filtered out. So that's why you might hook up a scope here, but you don't use these to produce an audio output. It's really just for looking at the wave shape. Finally, there has to be a meter on the front of this thing. And here it is. It's a very simple and classic half-bridge meter circuit when you're trying to measure something AC with a inherently DC meter movement. Here's the meter movement. It's a 200 microamp full-scale meter with a resistance of 1400 ohms. And there are two germanium diodes here which have a smaller forward voltage drop than silicon diodes do. If you take that into account and then figure out what the resistance is, because on the positive half wave the signal goes through this diode into the plus side of the meter and then through this resistor back out, but on the negative waveform this is a higher potential and it comes this way, same direction through the meter and then through this diode and back out. So that's when the waveform is low here. So either way, the voltage is always applied to the meter movement in the same direction, regardless of its polarity on the actual signal. If you do the math on this and subtract the voltage of the diode and put in the resistance of the meter movement and the 10K resistor in whichever half is currently conducting, you'll realize that it has about a 2.5 volt to a full scale. I erroneously wrote 2 volts here. It's about 2.5 volts. So when you have a 2.5 volt signal here, the meter should be at full scale. But we're taking this point and not only passing current through it to get the meter to move, but we're also feeding that back as the feedback to the overall amplifier. So that's how that works.